In the last lecture, we saw that the maximum a posteriori probability test, the MAP test, minimizes the average probability of error, where the average is taken with respect to this distribution Px. Earlier, we had seen that for all these hypothesis testing problems, for binary hypothesis testing problems, the the difficulty of the problem is determined by a distance between the two hypotheses. So the question is, which distance actually governs the minimum probability of error for Emery hypothesis testing? So HT is just hypothesis testing. So which problems govern the minimum probability of error for Emery hypothesis testing? Now, this may be an odd question because we have already seen that MAP minimizes the probability of error. So why do we need to figure out which? Uh, why do we want to? Why do we want anything more from that? We just know the best test. Well, it turns out this map is may not be easy to implement. Okay, and and this doesn't give us any heuristic about the difficulty of the problem. It just tells us one way of solving it, but doesn't tell us how difficult a hypothesis testing problem is. Can we look at the problem and just tell something about it? So, slightly more formally, is there some geometric notion of distance? So this is distance between what? They're now m distributions, w0, w1, w2, wm, corresponding to m different values of x. So is there a notion of distance that governs this minimum probability of error? That's what we want to understand. So we'll start with the heuristic argument. And most of this lecture will be about a heuristic argument, which will later lead to a more concrete theory. But just to remind you what's going on in this course is that all these heuristic arguments are for you to go and try and work out, so that you can discover these concepts which will present at the end yourself. These concepts didn't come out of the blue. Someone went through such arguments, the kind of arguments we are discussing in these classes, and then finally they discovered the quantities which are more concrete answers to these questions. All right, so we built some heuristics here. So look at this probability of error of g given px. This is the average probability of error. This probability of error is bounded above by max. So just a more elaborate description. It's the average over px. So how can error occur? An error can occur if you declare an x prime which differs from x. So all these y's for which the declared x prime is different from x will count as error under x. Okay, this is all calculation under x. So under x equals to x. Right. How many such hypotheses are there? There are m minus 1 such hypotheses. So you can replace this with max of x prime different from x, and there are m minus 1 such terms. So this max times m minus 1 is what you get here as an upper bound for this guy. But then there is no dependence on x, so this guy is just 1. So you get this bound. It's m minus 1 times max of x prime x this. So this expression is very interesting. We started with the Emery hypothesis testing problem, and this expression now compares only pairs of hypotheses, x versus x prime. What is the probability that the input was x, the unknown was x, but you declared x prime? So I'll just call it pairwise probability of error. Okay, probabilities of errors. Okay, so consider this guy now, this pairwise probability of error that we have discovered here, that we have come up with here. This guy can be written as 2 times this average probability here, that we can always do. Yeah, so this is just some rough thing I'm doing. So now this looks like a binary hypothesis testing problem with this small change. Under x you declare x prime, under x prime you declare x. Okay, so this is just the binary hypothesis testing problem with uniform prior. That's what it looks like. So this expression is essentially this expression up to a factor of 2, which we don't care so much about. So we can approximate this expression as, remember this probability of error was half into 1 minus total variation distance. So this guy here is just 1 minus total variation distance between x and x prime, and max goes inside, it becomes min. So what we have now shown is that this guy times m minus 1 exceeds pe star ex. because it exceeds this guy for every g, this also exceeds for p star px. Okay. All right. By the way, how did we get this? This is for some g, but the best you can do the actually this argument is, yeah, I could describe why this argument is rough here. The reason this argument is rough is because we started with the g, but this expression is for the best g. Okay, this expression is for the best g. So it's not clear if we can find this big G, this G for Emery hypothesis testing problem, such that for all of the binary hypothesis testing problem, this will essentially induce this best binary hypothesis test. So it doesn't matter. We are saying that suppose this can be done, so this is just some approximate thing. It gives us a simple approximate formula. So this is one heuristic handle on this, that this probability of error is roughly this much. It's very heuristic. Alternatively, we can use heuristics from Stein's lemma and approximate this error which came about here, right? This error here, we can approximate it by 2 to the power minus divergence between wx prime and wx. By the way, we only so how can we put divergence here? There was some other more elaborate form, large probability upper bounds on log likelihood ratio. Well, we are just using this expected value of that random variable as a proxy for its large probability upper bound. So that's divergence. So this is some approximate view of Stein's lemma, that this error is approximately 2 to the power minus divergence between wx prime and wx. Therefore, this m minus 1 becomes m. P, the optimal probability of error is approximately this guy. This is all heuristic. M times 2 to the power minus minimum distance. So there are two ways, and both bring out this minimum distance as a handle over P star. One brings out total variation distance, 1 minus minimum total variation distance. The second brings out 2 to the power minus m, 2 to the power minus minimum divergence. That's roughly the handle. So pairwise probabilities of error are handled by these distances, and minimum because the worst case hypothesis, the worst case binary hypothesis testing problem determines the difficulty of the Emery hypothesis testing problem. That's what we have sort of heuristically argued. So just in conclusion, so we basically need some notion of how spread out wx are in a statistical in some statistical distance, which we have to come up with. How spread out they are, that determines the error. So one notion of the spread out that we are considering is this minimum distance between wx and wx prime. So you can imagine that this wx and this wx prime are, this is my set of all distributions on y, and there are a lot of these distributions, w0, w1, wm. These are the distributions for different hypotheses. So we want to understand how difficult this hypothesis testing problem is, and one notion is how spread out they are. Here that spread out is being captured by which are the two closest points in this group. Okay, so the more spread out wi's are, the easier the problem. Okay, and one more point which comes out is that we can't distinguish more than this min. So in other words, if you want this probability of error, this is the bound you have for this probability of error. And if you want this probability of error to be small, let's say less than 1 by 10, some number I'm making up, then this m, the number of hypotheses that you can handle, is at most, so you can take log of m. Log of m is at most min distance. This is the number of hypotheses you can handle. So this is a very interesting perspective. Rather than asking what is the best probability of error you can get, we are asking for a given probability of error, how many hypotheses can you distinguish for this channel W? Okay, this is a very important notion, and these kind of questions can be answered in information theory. So heuristic calculation suggests that you cannot distinguish more than this minimum pairwise distance between x and x prime. Okay, so log of number of hypotheses you can distinguish is no more than this minimum distance. All right, but all of this was just heuristic. So this is just some rough calculations I didn't try to make it very formal. But these two conclusions, which are more qualitative, will stand, and it gave us some idea of how to characterize information revealed by y about x, and we'll build up on this idea. And in fact, in the next lecture, I'll right away give you the answer to this question, and then we'll come back and see how that answer relates to these quantities, the minimum distance, or maybe some other notion of distance can be used. All right. So see you in the next lecture.